Okay, thank you to be here for the lecture of today. Do you remember? I think, I don't know if you can hear me because I see something strange. No, it's okay. Do you remember we concluded with this picture in which we have here basically how change the minimum which the birds or the swarm, or better to say, the G-best, the best bird of the swarm, find over time. Time in our case is the step. We can see that at the beginning we have a relatively short stagnation in which the minimum does not change. But do you remember here directly from the initialization, we find almost immediately the minimum. Why that? Because the problem is convex. Therefore, I told you this example is an artificial example because I never suggest to use the PSO in case of a convex problem. The reason is we have more effective methods. I don't know if you heard about Newton method, tangent method to find the meaning. It doesn't matter. Believe me, I don't have time to tell you about. I don't remember if in this course I told you, but I don't think so. I don't have time to tell you about different methods to find the minimum. But of course, if the problem is convex, there is better method. What is the meaning of better? Method which is not so expansive in terms of numerical calculations. Because if you think about a very large swarm with many particles, of course you can say, but here is enough a couple of particles to find the meaning, of course. But in any case, even though with a couple of particles, we have better methods to find the minimum in case of convex problem. In particular, in this convex problem, we can calculate analytically. This means offline. We don't need a software which look for. Because you remember, if you have x squared plus 1, y equal x squared plus 1, we can find directly the minimum at x equals 0. Remember in high school, the derivative of y is 2x. 2x equals 0 means x equals 0 is in a parabola in which the minimum is at x equals 0 and the minimum is 1. We don't need to do this to learn this complicated, let me say, software structure. But why I presented this method in this form at the beginning? I presented to try to explain the method, to try to explain the limits. You remember, lower bound, upper bound, depending where, how I can define the lower bound, upper bound. I told you this concept of the density of elements. I don't know if you remember, increasing the particles have a different solutions because of the practically, nevertheless, the not convexity, let me say, show again what we have seen last time. 1 second. Nevertheless, in order to clarify better, is an interesting problem, practically, because practically, again, where is? Why I don't see? Yeah. Because practically we don't have a blue curve. Practically we don't have a red curve, even though the red curve represents nevertheless the reality. We have something like that because of the discretization of the surface. You remember the concept of the discretization because the computer works with an approximation of my mathematical surface. For the computer, does not exist a flat parabola and flat surface. I don't know if we can understand what I intend. It's just an approximation. You remember, we have seen the decimals in the approximation. This means we have an approximation which is something like that. X squared plus 1 is just, again, something does not exist. exists in a representation in a computer, which is stepwise constant. It's difficult to this concept, depending of the resolution of the software of the machine. You understand what I intend? Because we don't have an infinite small resolution, which guarantees a blue line. I mean, between this point and infinite small point on the right, we have here something which is not infinite small. Infinite small does not exist. Exists small. What is the meaning of small in our case? Is the resolution of the computer. I don't know if we're speaking about something which doesn't exist. I don't know if I told you about Nash. You know Nash, this mathematician, died some years ago. An American mathematician. He was, it's something which I can say because it is known. It was affected by this illness, schizophrenia. Yeah, but he asked the physician, but why you consider this an illness? For a mathematician, we are speaking about something, we are working about something which doesn't exist. In fact, I think nowadays we are speaking about psychological or psychic illness. If some subject is dangerous for the society, is dangerous with respect to other people, or dangerous with respect to himself. I mean, if I see a person is here, but nobody sees this person, I speak with this, but I don't generate any damage to anybody. I don't think so. It's in the modern psychiatry, they consider, in the modern psychiatry, they consider it an illness. I don't know. I'm not expert, but he answered and they said, why you say that I am ill? Every day I work with something which doesn't exist. Anyway, but I don't want to go ahead with this because I'm not competent, but exists something like that in the computer. What does not exist is this blue line. Eventually, we can consider this red line, which reflect something which is can be represented in this form. This is more, let me say, realistic. In which, do you remember I told you that depending on the number of the particle, we can fill down in some local numerical minimum, because theoretically is one minimum, but practically we have many. And increasing the number of particles, the probability that I will find the minimum here is higher. But also, this is an optimal problem. How many particles have the maximal probability to find the minimum? Do you remember I told you this idea? When people build my house in 1 year, 2 people in half year, for instance, 4 people in 3 months, 1,000 people never finish the house. We can see also here, because GBEST tried to orient this world. Yeah, but of course, if this worm is too large, it could be that, I mean, I'm not expert, but we can understand what I intend. Also, the number of particles, we can think, I'm not expert, that we have an optimal number of particles. This is also something which we can consider in our projects. Okay, now, let me come back to the simulation of last time, which is here, is in my YouTube channel. Anyway, we concluded with this concept of the stagnation. We have methods to reduce the stagnation, basically to give an impulse, better to say, to this worm, to move from a region to another one. Here we don't need, but because we are very quickly in the exploitation phase, because the problem is convex theoretically or practically, or better to say, practically not convex, but numerically not convex. We or with one step, or directly, it seems to me, with the initialization phase, we're almost at the minimum. Then you have a short stagnation here. I don't know how many steps. Here, a relatively long stagnation, but really, we can also stop here. When we have to stop, at which step? This is a big problem. But you remember I told you that in the software you can find the command iterations, you can find the form. I don't remember what I called middle iteration, in which we can nevertheless include some tests in order to say, please pay attention. Here we have in a stagnation. We can consider to put an input in the swarm. I didn't tell you what is the meaning of input. Rebound to mix again everything. If we think that we are not close to the minimum, is also an assumption. Or to stop here. In particular, here we can see that until 200 and 1,000 doesn't change much. Anyway, the criteria to stop is a difficult criteria. But you ask me, I think, what is the maximum? It's not important in practical application because we check I don't want to say at every step what happens. Here, for instance, starting from here, if you have an idea about the minimum, or if you think that this minimum could help you in your application, you can stop it anytime without waiting for the maximal number of iterations. You remember the example of the rotational velocity of the robot and translational velocity of the robot. If you have a reasonable value and the minimum of the roughness is enough for you, you can stop at every point. This means it's not really important, this one, because practically we'll never achieve 1,000, in this case, 1,000 in practical, because we have some checks. We check a little bit in order to see it is important to go ahead or not. I didn't tell you about the check. Maximal iteration, yes, but because otherwise too heavy the lecture. But in the project we can do, it's not so difficult. Okay, let me now send you per chat in a couple of files, which we will see again how this structure here, which I already told you, can be used also in a real example, or at least an example with real data, even though it's not the final software of the project robots to minimize the roughness, because this is really complicated. But anyway, it's a preliminary analysis which we did really. I will tell you in 1 second. Let me share a couple files per Zoom, and then we will start to repeat quickly the structure which you already know. We will see that really we can apply this. Okay. PSO. Okay. Now you can find the chat. I am using the chat because my study doesn't work, or at least in the morning, until the morning didn't work. You have now 3 files instead of 2. Do you remember in my study last time I introduced 2 files? Now we have another file because we have real data in order to show you how we can really apply with real data and how. Even though we can see the word simple, because yeah, for the lecture it's better, in my opinion, to present something simple to understand the concept, instead of presenting the final project. It is difficult to follow me. And we have also concept related to robots anyway. But this is nevertheless interesting. Let me see how I can move here. From here? No. 1 second, because also Zoom sometimes I'm not so able to manage in this sense. Where is Zoom now? Disappeared. Here. Oh. breaking. Okay, now. Zoom. Chat. Okay, here, no, where is? Confusing totally. Let me go out, otherwise, okay, now. Chat, okay. That. Okay, now it's going well. Here. 1 second, I come back. No? I am almost ready. Fitting. Yeah, it's this one. 1, 2, 3. Right. You have now in chat 3 files. I think I was able to do. For me, sometimes it is more difficult to manage this interface than to do the lecture. Okay. Let me open MATLAB and let me show you how it looks like this. Excuse me. Another question after this topic, at the end of this topic, I will introduce the parametric models. What do you prefer, to start with an economical model or an environmental one? Environmental. Economical is easier, at least what I have here. Even though the environmental one can be considered also in the context of the economical field, because in economics, we are speaking about prey-predators also, because in a competition system, we can understand. To start with the economical system is a little bit easier, in my opinion, because what I have in a linear system, typically I start with this to introduce the concept of the model. And I would like to start with this. And then we will move to a nonlinear system, which represents both economical and environmental, biological, everything. I don't know if you could, because if you start directly with the Lotka-Volterra, you know the Lotka-Volterra equation, because I have to introduce differential equations. I would like, nevertheless, to start with this economical system, which is the easiest, one of the easiest form which I have, and then moving. In any case, we have also 2 lectures in July. This means we have 1 month. That we have time to do everything. Okay, now let me share. Because I think that, but if you want necessary to start with Lotka-Volterra, I can do. But I think the majority of students, for the majority of the students, let me close this YouTube because I don't like. The majority, let me see, we have in a chat message. Please don't use. You cannot see the file. Is it not visible? Probably we had a delay. It could be that we had a delay. Did you have the file? Very important. Interrupt me without sending message in the chat, because if I am in Zoom, sometimes I don't see, it's not visible, the chat. I don't have signals which say to me, yeah, excuse me. But if you don't have, I can resend again, but I think we had a delay. We had a delay. Oh, like this now. It should be this one. Yeah. Why I don't see? Oh, do you understand this Zoom? No. No, it's really slow. The problem is really slow. Now it's working. How I can eliminate this now? Yeah, okay, I will see. Let me see. I don't understand the message. It seems to be that 2 times you wrote, we cannot see the files. Should I re-upload? You have it. It seems to be visible. You cannot, but you look in the chat. No, look in the chat. Okay, let me go to the files. Look, did you have these 3 files? Yeah. Now, look here. Let me open this main program simple. You will see now in a few minutes that the structure here is quite simple. In the sense that it's basically the same except for the dimension of the problem with respect to what I have seen before. Do you remember? Before we have seen the problem with 2 dimensions, and then we reduce to 1 dimension. We have the paraboloid with x and y, or x1 and x2. Y equals, you remember, x1 minus 2 squared plus x2 minus 3 squared plus 100. And then we reduce the problem to 1 variable. We had a paraboloid, and then we reduced to the parabola. Do you remember this? A little bit. With m, the first case equal 2, and m in the second case equal 1, in order to manage a little bit our considerations, to look a little bit on a problem which we already know. Now, we will see that the structure of the software is exactly the same, but I will tell you about the differences, why we have the difference. In particular, the differences here. Instead of m equal 1 or m equal 2, remember the first example again was m equal 2, x and y problem. I see some students who are perplexed. Look again here. We analyzed at the beginning of this problem, in which we found, I don't remember here, the minimum was x1 equal 2, x3 equal 3, or the vice versa. 100 was exactly the minimum, as a function of 2 variables. The dimension of the problem was 2. We have a swarm which moves in 2 dimensions. Basically, we have a matrix. Matrix represents the swarm with 2 columns and n rows. I don't remember the number, and 10, we try with 20. Anyway, we can put, we analyze a lot about the difference. If I put 10, if I put 2, if I put 1, I don't remember which case, in order to look what changes with a lot of, or less, more or less n. Here, we have in a column and a swarm. The matrix collapses in a column because the problem was 1 dimension. Now, in the problem which I try to explain now, the difference is just that we have the dimension 3. Why that? Because in this problem, let me consider now the main program. I will upload, we will see later, x data and y data, the measurement of what? We try to build in a cost function, which is a function of position on the surface, but just considering just 1 dimension of the surface. It's an easy example. And y are the roughness, which is correspond to this x position. I mean, it's already in a very simple example in which I don't consider the surface itself. You consider just 1 dimension of the surface and its roughness. In order to build, look here, the best regressor. Do you remember at the beginning of the semester I told you about the regressors? The best regressor, which fits this function, which is a function of y as a function of x, in which y is the roughness of the surface, and x is it's x dimension, one dimension. It's relatively easy because we didn't consider the two dimensions of the surface. Why is a non-convex problem? Because of the presence of this element here. I didn't tell you much about that, but believe me, if you have just one exponential function, we can transform in logarithmical form. Probably you heard about it, but if you don't hear, don't care about it. Because of the presence of this, we have a non-convex problem. This means we cannot separate what I know with what I don't know in the context of what I told you at the beginning of the semester. This means to calculate x1, x2, x3 is a very tough problem. X data is the position, the model which I consider an exponential function. We found this from the literature, but of course, as a simplification, because the model is in two dimensions, of course, because in surface, and consists of exponential function, consists of trigonometric function, because of the roughness, which recalls a little bit hills and valleys, but just to understand a little bit. And the idea is to find and why Bereknet, this is the regressor, which fits in the best way the measurements. Do you remember at the beginning this hysteresis curve? X and the y in the x-axis and y in the y-axis. Current in the x and flux in y. But of course, we have tried here, just didactically, to minimize the least square. You remember, I told you this is not really a good indicator because better to consider R square adjusted. But it is too complicated. It's not complicated, but to simplify it a little bit, the analysis, I consider this. But of course, practically at the end of the project, we consider a more complicated object function. But this, for the computer, it does not matter, believe me. Also here, it does not matter if I consider more complicated function. And in particular, if I consider also other dimensions, which must be considered in the structure of the exploration variable. X data are, as in a vector, the exploration data of the variable, exploration. And Y in this case is the output. But of course, I can consider also two vectors in the sense of exploration data, because the surface basically consists of two vectors in terms of exploration data. If I want to explore the surface of this table, I need this dimension, this dimension. Here's a simplification. I consider just this direction. And just this direction. But of course, I have to consider this means two vectors, one x and one y. It's a little bit more complex. We did. Okay, the idea is to show you how an fitting problem is an fitting problem with a regressor, particular regressor, in which I cannot formulate with this regressor and convex optimization problem, can be solved, this fitting problem, with PSO, because nevertheless is to find the minimum of this cost function. In this case, the least square, but could be also better in the sense, better cost function, this R square adjusted. You remember this. Now, let me analyze quickly the main. As I told you, we don't have differences, but of course, in LB and UB, you can see some strange values, because of course, you have to consider some real situation. This means we have to know something about the variable x1, the variable x2, the variable x3. I will tell you at the end of the result how we obtain this, This depends on my a priori knowledge. The rest of the program, when I change this, it's exactly the same. Of course, here I put n equal 5, but yeah, this is really just to test here in the lecture. Max, mean of W, which is again also here the representation, the weights of the vector which considered the velocity, but we can see maximum iteration 1000. We are considering just one swarm. About the number of swarms, yeah, this depends also the variations. I don't have time to tell you about the variation, but sometimes we can split the region, the search region, in different parts, and then we can involve different swarm with different characteristics to analyze one region with respect to another one. But really, this is complicated, and the project we can do together. But in the lecture is heavy, no? Let me consider just one. Everywhere, I will consider just one strategy, but you can understand that depending, if you have some a priori knowledge, I can consider structurally different as well. What does it mean structure? I told you what I intend. This global is a function which allows to read X data and Y data from everywhere, from this software here, for this program here, for the function. Load means call, or the load, better to say, the value which I have here in the MAT file. An MAT file, if you look help MAT in the command window, you can find how we can use this. But basically, it's in a function. It's in a file, better to say, which allows to save real data, measurements. But okay, this is a little bit more technical for students who want to work with real data, in particular engineers, but not limited to engineers. The rest, believe me, of the program is exactly the same. Look at this, for instance. This is the random initialization, let me say, swarm. It's exactly the same. I use exactly the same. Look here. Preliminary in the initialization part, I calculate the output function, which is another name, at the swarm. This is the little bit colloquially what I am doing here. Then I find the minimum. I save which bird find the minimum and the value. Exactly the same as I told you. I will save this best bird in GBEST, iteration 1, tolerance I don't use. You remember, while loop means while is closed with an end, not you remember. Between while and end, do everything what we have in the middle, between while and end, until the maximum iteration, less or equal maximum iteration. And the problem is exactly the same, also the comments. In order to tell you that what we learned is as a basic form is exactly what we can use also in real project. Of course, we can consider also different variations. If I consider different swarm for different regions, this means different approach. Here, this the equation can be for another swarm different, also this one. But the structure of the problem, of the software, if you remember last time, is exactly the same, just changing the notation. The unique thing at the end is that the regressor is different, but the structure is the same. I calculate let me say these two lines, considering this is the regressor at the GBEST. GBEST is the solution for X1, X2, and X3. And then we will, if you want to visualize, the solution is here. Let me see if I forgot to say something. I don't think so. Yeah, here's the tolerance we didn't use. I think here we used. At this moment, I don't want to go in depth on this because it's a little bit outside of our goal. Let me show you what happens. But if you analyze atom, you can realize that yeah, it's difficult really to interpret now the results. Therefore, you can understand why I told you at the beginning something artificial, but in which I can analyze the results. Here's a little bit the results. It seems to be that this regressor fits in the best way these measurements. A little bit strange. No? In fact, improving, better to say, the regressor, we had something that started from here, is going down here, and is passing here. But we need more than one exponential function. If you want, you can do at home with 2 exponential functions or 3 exponential functions, which can allow us to have basically something like that. But of course, with 1 exponential function, we don't have much variability. I think inside there is also tolerance and so on, but forget it at this moment, because I didn't tell you, I don't have time to go in depth on this. I don't want more advanced, but for us in this course, yes. Because for the examination, I don't, good. If you want to do something really exactly with the PSO, which we want to improve the method or the methods, of course, we can do that. But if you use in the context of another problem, otherwise too many things. But of course, we can understand that this regressor, in accordance with this regressor, is the best. If we assume that the PSO was able to find the optimum. Otherwise, of course, we can think that we have a regressor which is going from something like that through these measurements and then here. But with 1 exponential, we can understand we are constrained. Let me analyze the results and then we will conclude. Because the software is exactly the same, the structure. In this case, look at the results. This is the minimum of what? Of the least square, which doesn't say has much. Look at these 3 values. In your opinion, what we can say about that? The first thing which we can say, if they are inside the lower the upper bound. Because you remember last time I clarified very well, if we crash again the lower or the upper bound, this means that the PSO sees the minimum outside. This means it's reasonable to think to enlarge this, because the minimum, and the better minimum, is outside. Let me see. This means 100, right? The first parameter is 100. Let me see where is the first parameter here. It could be that this is in the lower bound, no? Of the upper bound, because it's strange, this value. Yeah, it's in the lower bound. This means probably we can find something better. Why didn't find? Because this is in the first example, and then we've improved the regressor. Again, this indicates also that the regressor is not suitable. A little bit. This here, let me see this one. This one is also on the border, in the upper bound. Look, 2, 4, 5. Again, 100. We can see it's here. This means the 2 values in the upper bound. Of course, we cannot accept. This element yet seems to be not so bad, because it's inside these limits here. 10 up to 4 until 10 up to 6. Yeah, it is. It is. But of course, 2 elements outside of the boundary indicates that the minimum is outside. Can also indicate that the regressor is not very good to find the minimum. I don't know if it's clear what I intend. In fact, if you look at the results, we can assume that we have something better. Here, in a curve that starting, I don't know, from somewhere, is going down here, is going here. But of course, with just one of exponential functions, it's impossible to find here. But it could be that we find something better. Also, with this not really appropriated cost regressor. Let me decrease this, no? Because you remember, I found a minimum in 100. This means the PSO sees the minimum outside. I don't know if it's clear what I intend. Last time I told you this stupid example. If I say to you, look for my key in this room, but the key is outside, you crash again the wall. The wall. At least PSO crash again the wall. You say to me, it's not here. I don't know if it's clear about it. Let me say 10. And let me say here, instead of 1,100. It could be that nevertheless, excuse me, instead of 100, 1,000. It's clear what I intend, because PSO sees that the minimum for this parameter is less than 100. Because crash again the wall. It's outside of this room. And for this parameter, is outside of the room from the other part. It could be not, not necessarily it works. If we put infinite and with this work, of course, we can think really that as it is, that the regressor is not able to find inside this interval the minimum. But it's quite clear, but it could be to find something. Because did you see that structurally the regressor is strange? Let me run. A little bit better, we can see. Look at the picture also from home. Do you remember at the beginning I told you this could be possible, make more sense, it should be better than before. In fact, we can see the object function, the minimum is not 5, but 3. Let me see if we are nevertheless on the board. Because if we are on the border, we are not in the local minimum. Of course, we can stop also here if we are satisfied. Satisfied of what? Of the minimum which we have. At this moment, don't care about this value because it's not normalized. Anyway, assuming that for you, you know the minimum. Look, now here inside. Because, no. Let me see. Yeah, it's inside, no? 2, 4, 6. Yeah. 304 is between 10 and 1,000, right? Let me see, because from this distance, yeah. If you multiply by 6, no? Excuse me, by 10 up to 6, this value we have, let me, because I don't see where 2, 4, 6, we have a 304, which is inside this interval, right? Please pay attention. If I change the interval, change everything. This is a little bit it's difficult to explain, but think about that this kind of problem is a non-convex problem. Anyway, this is internal here. This here is now on the border. Yeah, is on the border this. Because this is 10 up to 6. Like this. It's a little bit strange as I wrote, but this here is inside, right? Because 2, 4, 6, 50. No, it's on the border. Okay, we can see that nevertheless the value is better because before was 5. That's 3. But nevertheless, we have already we have still value on the border. We can try again, but as I told you, it's the regressor that it seems to be not valid. Let me write something here. Let me write something here. Increase, no? Enlarge. I enlarge this, reducing. I enlarge. I reduce the LB for this one, from the third one, yeah. And I increase in the upper bound of this, of the second value. It's clear what I'm doing, but not necessarily will work. Let me see. Absolutely not good. Now we can see also here the value. What indicates this? Exactly what I told you before. We are using a regressor too easy. And PSO cannot find an appropriate function which inside the interval find a minimum. This is an indication that, in fact, is a too easy regressor which we are using for this problem. And in fact, we use more exponential functions, sine and cosine and so on, with more parameters. Yeah.
Now you're enlarging the range, right? Why doesn't it just find the old function that we just had again? Because it's still in the range.
This is a really good question. You say, at least should be find the previous one. Mm-hmm. The reason is that with this simple structure, we fell down in another minimum, which is not better than before. Why? Randomly. Because not forget that the program is a random program, a random structure. No guarantees. Increasing the particle, it could be that we find. Because look, another limitation which we have, good question. The question was, but why I didn't find the previous one? I just enlarged. Yeah, why? In this region, even though the region is enlarged, randomly, probably because of the limited number of particles, we fell down, we ended up in a minimum, which is worse, it's not good enough as before. It could happen. In particular, when the number of particles is very small, in this case. Question?
But if we now improve the iterations to a very high scale, then it's more likely to find the old result that was better, right?
It could happen. Try to do at home, but what I will do for now, and then we will go ahead because I have to try to increase the number of particles. This is because of course with 5 particles, even though you enlarge and then you say, oh, why did you find it? But the problem, the search is random. This means it could be that in particular in the exploration phase, this worm is going in a valley which is not so good as before remain there. Now, with a larger number, it could be that we find at least something similar as before. You have to imagine this problem. You remember this picture which I put at the beginning with many valleys, many hills, something like that. This means it could happen that even though I improve improve and enlarge a very good, excuse me, I'm distracted now. Let me run. I enlarge, I'll not necessarily fall down in the solution, which is nevertheless there. Let me see. Now better. Now, did you see it? Did you see it? Yeah, now we are inside. Look, now we are totally inside. This means you can understand, it's intuitive, that the number of particles plays a crucial role, is important role. But of course, try to do at home is very nice exercise. Look, why we are inside? Because here we have 289, right? I have to multiply by 10 up to 5, 2, 4, 5. This means we are inside here. Here, definitively we are inside because we have 6,000. Yeah, this is the value. No? yeah, inside 69,000 and so on, no? Right? Then up to 5 I have to multiply. And this definitively, because it's 35, no? 2, 4, 5. Because it's between 5 and 1,000, right? Did you agree that every element which you're looking for is inside? This means this solution here, it could be a possible acceptable solution with this simple regressor, but including more exponential functions. We will try to do at home. It's too difficult as an exercise. Try to do at home to consider another exponential function. This means x up to 4. With x up to 4, the dimension is not 3 and 4. We will see that better and better if you look at the minimum. The minimum at this moment 3,3. Let me say 3,3, because it could be that we can obtain something better. No? We have the slope. I would like to increase the slope a little bit. It's interesting, this example, even though nobody knows what is the solution. It's PSO. I told you already, with PSO, we can do also PhD programs. In Stanford University, Stanford is not the worst one. Yeah, if you look at PSO, particle swarm optimization method PhD programs, they have a lot of PhD theses already done. If you look, it's an extremely important algorithm itself. It can be applied everywhere for stupid problem, for more complex problem. I like a lot. I'm not expert in optimization because I'm an engineer and not mathematician, but I use a lot. Next year will appear in a book written from me and a student of this course, which is going ahead with another program, to say not here, and the student who received the best paper award. I will send per email the paper, the best paper award received from complementary study. Okay, now let me close with the PSO because I have to go ahead. Let me start with the concept of differential equations, parametric model. I would like to start with the economical system because I love me to introduce. Did you agree until 8 p.m. half hour? Did you have time? Half hour for me? Do you have time? Yes. Because I would like to start with this new topic, and then the last topic is the Lotka-Volterra and control of Lotka-Volterra. No? You will see the control. So Lotka-Volterra can be used also for economical systems because in a competitive, but also for biological systems, for population dynamics, everything. I will try to. Okay. I hope that this is interesting. Could be also formulate. We can formulate also problems. Yeah. I don't know if you have a question me. It's too difficult. Try to do at home. Try to do at home. I like a lot because it's also sympathetic to image this worm that is moving. And again, on the thing does not exist. No? The swarm, we can see the swarm as in a matrix with different dimensions. Okay, let me find the material. Before find the material, let me stop a little bit so I have a little bit more time. As I told you, now we will start with a new topic, and let me share. The rest of the course will be dedicated to what happens now? Really, this Zoom, yeah, dedicated to the, I would like to say, to modeling and control of dynamical systems, and in particular, systems characterized by parametric elements, I would like to say, or the parametric models. As I told you, parametric model means that the parameter have some particular meaning. The physical meanings or particular meaning is physical is limited basically to the technical systems. But of course, what we learn until now, everything can be used inside or to realize in a model. To realize in the model. The meaning of parametric model, we will see also today. I will start with this lecture, which we can see is dedicated to not engineers, is inside another course. But let me start with an economical system, because it's easy to, let me say, to be presented. And then we will conclude the course with an Lotka-Volterra. I explain a little bit better how we can use also this Lotka-Volterra in different fields and the control of Lotka-Volterra. But the control can be applied also here. But I will not tell you here about the control, but I will tell you in the context of the Lotka-Volterra. I will tell you about the nonlinear control strategies. Here, the method can be applied, which I will tell you for Lotka, but in this relative easy, at least for this relative easy example, can be applied also different control strategies. Why I am telling you about this? Because this is a possibility to introduce a system which is a concrete system in an easy form. Look, bank account system. We can see deposit, we can see expenses, even though this arrow in this direction seems to be strange. But if you consider this d of t in this direction, d of t is negative, no? Because I withdraw money. No? U of t is an input. I put money in the bank. L of t is the variable, which increase or decrease over time, depending on the bank account system dynamics, depending on the deposit, depends on the expenses. This arrow in this direction is just a convention. I will clarify a little bit later what I intend. Practically, it should be better to put deposit exactly as is indicated, expenses in the other direction, and this capital over time, I would like to also indicate in the other direction, because it's something which I have at disposition, which can be considered as my output, what I have. But believe me, the direction of the arrow is totally free. In any case, if this is the direction which I want to consider, the deposit I would like to consider positive in this direction here. But if I have a withdraw, I made, we have to distinguish, I'm not expert in this, but between expenses, the expenses is not necessarily withdraw money. Withdraw is an active action. I take money. Expenses could be also some expenses which is fixed by, I don't know, I have to rent my apartment, to pay for rent of my apartment. I have to pay for a credit. In any case, if you want to consider this direction, in the sense that expenses should be in the other direction, or d of t is negative. I don't know if you have, we are familiar with this sign of the arrow in the system. Probably engineers, yes, no, if you think about voltage, current. But let me go ahead. We have this deposit, it could be positive or negative is withdraw. We have expenses, which in any case, let me say negative. And the capital over time is not also wrong to indicate in this direction, because in the bank, this capital which is in the bank, but belong to me, please pay attention. The name is liability, meaning the liability is something which belongs to me, but is not in my wallet. It's not at home. This is characterized the bank system. Because if I have money at home, I cannot speak about a dynamics of the system. I will clarify in a few minutes. Now we have many information here. I try to simplify. Because this is in a slide in a course for another auditorium, I would like to say. Look at directly at the end. When we have this equation. For the engineer, it's quite easy, this equation, because recalls and the circuit. I don't know if you remember this. An equation of the first order, which you have an x derivative. X derivative means x, the derivative with respect to the time, equals the parameter a multiply x plus u. If you remember in math, this is an equation which we can solve somehow. If this beta multiply IL is given, if U is given, it's a linear equation. I'm considering in this model as a linear equation. This means we are considering the liability L in the context of a linear model. It is always not so, but just to introduce the concept of the parametric model. Parametric means that this beta IL, I come to you, is a parameter which is a particular meaning. The meaning is here. Question me.
It's like
Don't care about them, not expert in economy. I copy from a book. I think it's not wrong, but I, as a system theory expert, let me say, I'm not really able to analyze. Probably you're right, but I think together with IL, it is an example. You see, example. Really, if you are expert in economics, probably you can correct me as in a parameter like IL, which states how in the contract you have to sign an agreement. I don't want to sign a contract, but also in a contract, an agreement with the bank in accordance. In the sense, if you look at IL, is the interest on deposits that is the bank liabilities L of T paid by the bank. Yeah, it is. Exactly. I would like to interpret it. So about beta is a little bit more obscure what is, but then we publish also the paper with an economic student because about bank, I don't have any idea. In fact, at home, I delegate my wife for everything. But think about beta multiply IL is the interest, it is netto interest which you receive. Now, nevertheless, now I clarify the wording of parametric. That's the meaning, clear meaning, beta multiply IL. Do you remember when I told you not parametric model, this regressor, not always we have a clear meaning what is. Now, if you look at this model here, U of T in this context here is dollars, money, euros over time. This means it's what I'm doing at the end of the day, per day, what I put in my bank per day. Also, this expression here is liability over time. This means how change the liability over time is a function of this element here, which is liability. Liability is the money which is in the bank but belong to me. I don't know if it's clear what is this sense here. Because if the money is at home, we cannot write this equation because the money at home remains the money at home, does not change. Here, change, even though U is 0, even though I don't do anything today, even though I don't do anything tomorrow, even though I didn't do anything before yesterday, change if, of course, I have a liability at time 0, not 0. I mean, if I have money in the bank, even though I don't do anything, we have the dynamics. We hope that the money will increase. If the money does not increase, probably I can think to take my money and to put at home. Because if I don't have any, let me say, in a suitable dynamics, why have I to put the money at home? Of course, they say you can be sure that the money is here, we cannot lose. But this is a little bit the idea. Question me. Of course, beta on IL can change. Yeah, the derivative. Yeah. How your money, this is the derivative. This means exact changes over time. Your liability, your money, which is in the bank, change over time in accordance with this law. Could. Of course, it's a little bit more complicated because we have inflation is not included here. We have just to start with an easy example. We can improve. In fact, in the paper, we improve the model, but just to introduce the concept of dynamics. If I have a liability at time 0 when I start, not 0, even though I don't do anything, if beta multiply IL is positive, my money will increase. I will go in depth on this in a few minutes. We have 10 minutes to go ahead. Forget a little bit this it's a little bit heavy. We will come back. Look now. I have this model in the middle. But the bank is in a system which is organized at least per day. Now you can obtain the amount which you have, you can update your amount at each time, but before this method that we can update just at the end. Sometimes it also works. So even though you do something during the day, you have the result at the end of the day. In any case, the interest is not calculated at each time. It's calculated per month, per day. Depends. In general, the investment, the interest is calculated per year, per day, but not for at each milliseconds. This means if I put the money now and I withdraw in 1 minute, the money which I put is the same. This means the interest change, I don't know, each 3 months. You understand? This concept of the changes of your liability is summarized here. TS is the simple time. Is the time in which in your contract is written, I will give you somehow the interest each 3 months. This means this model here must be considered in a particular form. The particular form is the discrete form, in which I try to discrete the model or to realize the discretization of the model in accordance with this idea that the variable change not continuously over time, but change each TS time, each 3 months, or at least the updated of your liability with respect to the bank point of view. Look, if you consider that the money L of t can be written in this form here, L of k minus 1, and the input can be deposit or withdrawal can be written in U of k minus t, in which, if you don't like, so think about k of minus 1 multiply t of the ts, no? As I put you everywhere. But typically we didn't put ts here inside. But if you consider k from 1 to n, we can see that we have value at the first day, the second day, we will see next week, and so on. Very important is the derivative. To approximate the derivative, considering the liability today, tomorrow, means the liability today if L of k minus 1 is the liability today. Of course, we can consider also L of k minus 1 the liability of yesterday, and L of k the liability of today. If you consider this possible approximation, if you put here, you will obtain this. Next week, we will go ahead and restart it from here. Just a few words. I copied for you again this equation here, which I tried to explain quickly in the previous slide. And look here, from this equation here, it's easy to calculate this. Now, here we can understand a little bit better this discrete dynamical system, which came from the discretization of this possible dynamics of the liability. I mean, look, the liability of today, if this represents today, equals the liability of yesterday. Again, the liability is the money which belongs to you, but is at the bank, in the bank. What they have yesterday, plus the multiplication of 1 day, assuming that is 1 day, considering the interest which we have in the new contract of the money of yesterday, plus what you did during the day. One, which you multiply, if you put money, if you withdraw money, everything which you did in the time TS, which could be 1 day, could be 1 month, it depends of, let me say, of your contract. This we can understand in the sense very well. Now, let me understand this. This is 3%, and this year is 3 months. But in this case, we have to understand 3% for what? Each 3 months. This means TS is 1 in the sense, no? Because the sample is 3 months, but represent the unit, let me say, the interval of time which I consider is 3 months. This interest, which is 3 months. And also here is 1, and this U of K is everything which you did in these 3 months to calculate what we have at the end of these 3 months. This is exactly what you had at the beginning of these 3 months. I will come back next week to go a little bit more in depth, but this is quite clear in the sense, look, I will increase my money even though I didn't do anything, even though I will not do anything, depending on this value here. We will see a little bit together. Let me say next time what I would like to say. Let me see if I forgot something. Yeah, we can see very well that this element here should be larger than 0, no? Otherwise, I will not increase. Okay, we will come back on this. I will repeat a little bit. And next time, I don't know if I will tell you about the Becquerel-Euler approximation. This is a possible approximation with the name in the Forward-Euler. I didn't emphasize this because I don't think so that I will tell you about this possible different approximation. Next week, we will go ahead directly from here, which we will consider the assets dynamics, and then the combination of assets and the liability. Yeah, to show you a little bit this kind of let me say, this kind of system. And nevertheless, next week we will conclude with this easy example, and we will start with Lotka-Volterra, which is more interesting. But nevertheless, it's important to notice to introduce the dynamical system using this particular bank, this particular example, which is a bank system, in order to introduce the dynamics. But of course, we can also consider the project in this sense here, starting exactly from this model here, even though my idea is to extend during the project an economical system, but non-linear. Therefore, Lotka-Volterra is more important than this one, but this is allow me to tell you about parametric models, differential equations, and so on. I think I have time next week also to simulate. Thank you for your attention. I'm here for students who contacted me per email in order to discuss a possible project, even though it's nevertheless early, because these topics here, parametric modeling, and also Lotka-Volterra nonlinear control or general control is nevertheless an important part of the course. I am here. Thank you.
Nice.